Up next, we're going to be taking a look at embeddings. So embeddings are a way of interpreting the structure of your data in a certain feature space. This aligns more with unsupervised learning techniques. So some of the methods available in TensorBoard are the likes of PCA analysis and t-SNE. And we'll see an example of how we can look at embeddings for the MNIST dataset. So here, to work with MNIST, we need to have some kind of embedding or feature space that represents each of the samples. What we're going to work with here is just the raw pixel values. For other datasets and other models, you might have a clear embedding layer that you want to use. So Word2Vec, for example, has a clear embedding for every word. So that's a more appropriate example. But just to keep things simple, we're going to work with the raw pixel values, and that will be our feature space. So clearly we've got a large number of features. In fact, for MNIST, I think we're working with 28 by 28 pixels. So we're going to times those two together, and we're going to have quite a large feature space. But that's okay, because these methods can work with high dimensional data and reduce that down into the 2D and 3D representations. So let's see how we can go ahead and use the embedding within MXBoard. We're first going to load the MNIST dataset straight from Gluon Data Vision. We're going to use the training dataset, and we're going to do some simple transformations. So here we're going to flatten the data, and we're going to divide by 255, just so the pixel values are in the range between 0 and 1. Next, we're going to create the data loader, just so we can get a random sample of 2,500 images. So we set our batch size, and we use that in our data loader, and we set shuffled equal to true. So we've got a random sample. We only take a single loop through our data loader, and we specify all the variables that we'll need later for our embedding. So as mentioned before, we're just going to be working with the raw pixel values for our embedding here. So we set our feature space and our embedding to the data itself. Next, we have to specify the label. So the label helps us tag the points in the feature space in our visualization. So here we're just using the label straight from the data loader. For MNIST, it represents the true value of the handwritten digit. And lastly, we've got the images. So this is really useful for the visualization itself. Instead of having random points in the feature space, we can denote a point by the image itself. Because we did the flatten earlier on, we're just going to do the reshape to get it back to the original image. And now we've got the three components that we need. So with a summary writer, opening the context, setting the log directory, we call the add embedding method. And as with all methods, we want to specify the tag, just so we've got the label, and we provide the three variables that we created above. The embeddings, which is the feature space, and we've got the labels, and lastly the images. So we'll go ahead and run that now. That's saving everything to disk. So one thing to note, with embeddings, I found that the server often needs to be reset for the tab to appear, and the tab is called the projection tab. So let's stop and start our server just so that appears. So if we go back to TensorBoard, we can refresh, and hopefully we will have the tab appear. So here we've got the projector tab. So let's have a click on that. And this will load in all the data that we've just processed, and we should be able to do some visualizations. So by default, it's going to do PCA analysis and visualize the first three principal components to give you the most variance between all the points. We have a nice rotation effect going on by default, so we can see our feature space, and we can zoom in and out of this point cloud. And you'll see the points are actually represented by the images themselves, which is really handy to find clusters and do the visualization. So using PCA, we can see that we've got a cluster of ones down in the corner here. You can see most of these are ones. And maybe in certain other areas we've got lots of 9s and 7s with different shapes. We can use our labels that we use to isolate points in the cloud. So say we want to see where the 2s are. We could just type 2, and in red we should be able to see the 2s. They're kind of across this side a little bit more. Again, we could search for 1s, a little search, and they're along on the other side. So this PCA is giving us a good split between our data. We can color code images as well. Instead of searching for certain labels, we can add a color map. So here, color by, we can select the label, which is adding some extra metadata. And now all our points have a color corresponding to whatever label was used. So we have a section of zeros we can see down here. So PCA is one method that we could use. Another method is teasney. So we can choose our method in this section on the bottom left-hand corner. This is all going to run on through the browser, so it's going to be relatively slow if you've got a large data set. Just something to be aware of. And now teasney is an iterative method, so we run the iterations and we see how the point cloud changes and see how we get the clusters. So we can just stop it now and have a look at our shape, and it's managed to split out the categories quite well. And this is just generally helpful in working out how decision boundaries may be made by your model. You might get lots of examples that are quite similar. So maybe the 4s are similar to 9s because they're quite close together. We might get some points that would be cross the decision boundary. So it just helps understanding your feature space while working with machine learning models. And this is a great way to do that analysis. If you're creating embeddings, such as word-to-vec embeddings, you can check for semantic similarity, just to make sure things make sense, and you can do the visualizations there. Or instead of the images, you can have the words represented. So that's another option. And lastly, there's a limited amount of tools that can be used to isolate different sections of the data. So here we have the bounding box selector, which you can use to draw regions across your data and find the specific samples that are contained in that bounding box.